I am going to talk to you today about this MCP server I put together this summer, which I've titled MANNA, which stands for MCP Architecture for NOIRLab and NRAO Archives. Um, and yeah, it was part of the three-part stable CosmicAI summer project. So diving in, just to kind of outline the problem at first. So among all of the various astronomical archives, many of them are built on top of a similar set of standards, IVOA standards, but they, by and large, have different schemas and query syntaxes, and they're, overall sort of a non-standard implementation of the same set of standards, which can make knowing multiple of these archives pretty challenging. And that has effects on multi-wavelength astronomy. It means that you have to have a pretty deep contextual knowledge of each of these specific archives. So it makes multi-wavelength astronomy tricky. It also, if you're just trying to do some like preemptive exploratory work, whether you're like thinking about submitting a new proposal for observations on like a telescope that you don't usually use, can also make those like intro efforts challenging as well when you really want to have them be like pretty quick. And just as an example of how like this problem manifests is if you had a question like here, which is which of the 12 nearest luminous infrared galaxies observable by both ALMA and the VLA still lack millimeter data, but already have radio and deep optical coverage. This is, kind of like a standard question somebody might ask, especially if they're looking to fill some gaps in observations. But this means, queries to 3 different archives. Each of those archives have different schemas and they have different interpretations of ADQL. And there's a lot of kind of contextual information that you need to be able to fulfill this. And, looking at 12 different, the 12 nearest luminous galaxies, like this would end up requiring around like 40 different queries to these different databases. So that is just sort of a big effort here. And we determined that LLMs, can be a convenient solution to this issue, especially in like in using a custom MCP to augment the LLM's like native abilities. So I'm not going to go over in too much detail what an MCP server does. My guess is that many of the people on the call already know, but in general, MCPs are these like usually small, pretty lightweight packages that you can use to augment LLMs. You can equip an MCP with a set of tools where a tool is really just either some like contextual information that an LLM can gather by calling a tool, or some snippet of code that can just be Python code that is, that the LLM can then run. And this is convenient for accessing astronomical archives because they are built on top of similar protocols. Many of them are, some of them aren't, but many of them are built on top of these IVOA protocols. So we can use these kind of flexible tools with a little bit of tweaking based on specific quirks of each archive. And that way we can have this, one centralized source of information that will allow us to gather data from all these different astronomical archives. And MCP servers are also really nice because they're fairly flexible. Not only are they, pretty lightweight, but they're also flexible in their deployment options. There's a lot of different ways to use them. You can integrate them into like a science platform, which I'll talk more about how we're doing that right now at Astro Data Lab. Or you can use them on your own machine, whether it's on Claude Desktop or Claude Code or Cursor, whatever your agentic client of choice is. they're really flexible, and as it stands right now in the AI landscape, they're one of the most versatile ways of extending LLM performance. So that's what we did this summer. I spent the last 3 months building MANNA, um, and provided it. It's overall a fairly simple piece of software. It just consists of a set of under 20 different tools, some of which provide uh, like inject context into an LLM's agentic workflow. Some of them are query execution specific tools. So there's different tools for tap queries and simple image access queries and things like that. They're all built on top of the IVOA protocols. So that is a prerequisite for introducing a new archive to MANNA. It needs to be built on top of IVOA in general. And the package is lightweight, stateless. So there's currently no like authentication or retained data between different calls. And it's also we've set it up to be quite maintainable for future deployments and ongoing maintenance and things like that. It is flexible to any IVOA based archive. You could also include tools that for non-IVOA based archives, but that would have to be kind of a custom thing. And one of the things that I spent the most time this summer on was building an evaluation framework to quantify the MCP quality. Because the thing with MCPs is they can be quite easy to build initially, but it's easy to build one, but it's hard to build a good one. And as it stands, there's not really a widely agreed upon framework for testing MCP quality directly. There's obviously benchmarking with LLMs, but testing an MCP directly, requires you to be pretty granular about looking at which tools are being called, making sure it's calling the right tools, overall robustness of answers and accuracy. So put a lot of work into an eval framework. And you don't have to read the entire slide here, but this is just to kind of give you an idea of how MANNA and its tools, are used within an LLM's workflow. So on the left here is kind of this like chain of thought of an LLM. And at each step, it calls a different tool from MANNA, from which it either gets like archival context or it executes a query. So this is kind of a simple example, but the general idea is that, at each step here, an LLM is able to get more information that it needs cheaply. So, these days, frontier models are capable of doing an entire workflow by themselves without like an additional MCP server. But what's great about MCP is that it provides the most direct route to the correct answer for these LLMs. So, that manifests in lower token costs and like lower iterations, and you don't have to worry about silently getting the wrong answer. I think one of the big concerns about using LLMs to query data is that a lot of times like the failures are silent, like if you're using the wrong ADQL syntax, you might return 0 rows from a query when actually that 0 rows is resultant of an improperly written query. So you need to make sure that you have as much information upfront as possible when you're calling these things correctly. So just to quickly talk about, how this server is actually functioning, we put together this evaluation framework. There's a couple different tiers. It's testing tool selection, task success, and robustness. And these are each essentially like their own separate tests. They are are meant to represent realistic archive tasks. And each one of these tests has, like a ground truth answer that's been verified. And with this evaluation framework, I was able to kind of, do some A/B testing with and without MANNA. So I ran this evaluation framework using MANNA and then turning MANNA off. There's a couple different options. I provided it with like a simple tap tool in one of these, one of these evaluation modes. And then in the final mode, just, basically gave it access to the internet. And these are the metrics that I collected from those evals runs. In general, we're looking at I ran this on Qwen 3.5, the large language model. And I saw about 3 times fewer tool calls, double the overall accuracy for this subset of archive task tests, and quite a few fewer failed calls. And that again just means lower token cost. And I saw similar lifts across a number of different models that I tested. So we tested Qwen 3.5, Nematron 3 Super, which is NVIDIA's current open source model, and Haiku 5. We're planning on doing a more in-depth evaluation analysis with some of the frontier Anthropic models, but that's, I think, going to happen in the next week or two. It's obviously more expensive to run those evals, so we want to make sure everything is tight. And to talk about how this is actually going to get deployed, right now we're actively working on deploying MANNA in the Astro Data Lab platform. We're essentially, so Astro Data Lab has its own Jupyter notebook aspect. So you can like go in there, work in Jupyter notebooks. And I've worked in the past month or so in incorporating Jupyter AI, which allows you to use a chat window that is talking to an agent within that notebook instance. And it's able to, create notebooks, edit them, run code, all while interacting with an agent. And we stood up a locally hosted Nematron 3 model, which we're currently testing it against. And yeah, at this point, we're kind of working out some kinks and making sure that all the security is up to snuff, and planning on eventually rolling this out to the larger community who uses Astro Data Lab. And then in general, also planning on deploying this on TAC as a remote server, and uploading it to PyPI so that people can install this or configure their whatever your agentic platform you use on your local computer. You can configure it to use this MCP server directly. So there's a couple different ways to do that. I won't go into the details there, but this makes it so you can just use it on your local computer. And to kind of walk through, I have a couple demo slides here. This is what what Jupyter AI looks like in a Jupyter Hub type platform. So there's a chat window, which is on the left, and then the chat window is directly, working in this Scratch notebook on the right. And I provided it with this query using Astro Data Lab archives, get NSC DR2 sources within 6 arc minutes of the sculptor dwarf galaxy, and plot a color magnitude diagram. And this was run using this open source model that we have hosted on Astro Data Lab GPU right now. It's just that open source model and the MCP server set up next to it. And if you scroll up on this here, you can see there was something like 15 different MANNA tool calls that this session used. So it was using them, it was sort of learning as it went, and it was able to put together this color magnitude diagram rather cheaply. Yeah, and there I also have an example for running MANNA on like Claude desktop. It integrates with Claude Code as well. But honestly, the best way to do this might be just to show you quickly. If we have time, we can go through this at the end. But this is just to show how MANNA can, augment even frontier model workflows. I ran this using Opus 4.8, and it really leaned heavily on the MANNA tooling and produced I think a pretty good result, which I'll show you guys after if we have time. Oh, okay. So just to wrap it up here, I think I'm at time. We determined that MCP can dramatically improve AI agent performance for accessing astronomical archives. I think that was proved through our evaluations run that we did. We've been testing it out in a number of different ways, both through the Astro Data Lab, Jupyter AI deployment, also through using it with agentic platforms like Claude Code and frontier models. And yeah, the final step here is to clean this work up. I'm in the process of moving MANNA to the CosmicAI GitHub organization repo. So I think it's probably gonna get split into a couple different repos. But when that happens, I will share it with the team, and I encourage everyone to use this in whatever way would help them in their workflows. And yeah, I just wanted to say thanks to all these amazing organizations, CosmicAI, NRAO, Astro Data Lab team, and our stable team. And I'll open it up for questions.